morning, everybody. First talk this morning is going to be by Kious, going to speak about random walk and symmetric exclusion.
Thank you. Thank you very much to the organizers for this conference. I've very much enjoyed it so far, and thank you for letting me speak. So yes, I'm going to talk about the random walk on the exclusion process. So the random walk on the exclusion process, it's a model that falls into the class of random walks in dynamic random environment, right? So you probably know, I mean, you have heard about random walk in a random environment since Monday, right? In Balin's talk, in Felix's talk, and you can see it in Z. Okay, I'm going to talk only about Z today. You can see it as a random walk on top of a random potential, right? So you have this particle, this red particle, that is traveling on this random landscape. So it will roughly follow the slope, but it will have its own erratic motion as well, but roughly follow the slope, right? So that's how you can see random walk in random environment in dimension 1. If you want to look at a random walk in dynamic random environment, then what you do is that you let this potential wiggle with time, okay? In the same time as the particle is moving around. Okay, so now I have this potential wiggling and this particle moving around at the same time. Okay? And what the physicists like to consider is the case where the potential moves diffusively with time. Okay, so what it means, you can think about correlations created by the potential in the model. They should be diffusive. Okay, or the mix in time should be diffusive, quadratic. So that's the model. So how I'm going to define this potential today is using this exclusion process. Okay, and the kind of questions we're going to look at is, do you have a law of large numbers, CLT? So this is the kind of question we looked at a few years back with Augusto Teixeira and Marcelo Hilario. And the result I want to mention today is going to be about the strict motoricity of the speed, okay, which is hard to obtain, and I will argue that it's actually a sharpness result about this model. A sharpness in the same sense as you would talk about in the percolation theory. All right, so, and that's the joint work with Guillaume Cochon-Kerjean, who I think most of you know now, is a lecturer at King's College, and Pierre-François Rodriguez, who all of you know. All right, so I'm going to define the model now. So first I'm going to define the environment. So that's the exclusion process. So I'm going to need a couple of parameters. So I need the rate mu. Okay, that's my first parameter. It's going to be fixed for the whole talk. So, okay, you can fix it in your head and that's it. And there will be a density, rho, which will be more crucial in this talk. I'm going to play a lot with the density. Okay, so what's the exclusion process? It's a Markov process on 0, 1 to the z, meaning you look at z and each point of z you either put a 1 or a 0, you put a particle or a whole. All right? So it's a Markov process, so you need to initiate it and you need to give the dynamic. So to initiate it, I'm going to choose at time 0 a product Bernoulli with parameter rho. Okay, so at each site you put a particle with probability rho, you put a whole probability 1 minus rho. Okay, so that's the initial configuration. So you have that here. And each site you put a particle probability rho or whole probability 1 minus rho. All right, so you have something like that. Let me add one here. All right, and now what's the dynamic? Well, it will go in continuous time, and each particle is going to have its own exponential clock with rate mu. And when the clock rings, so they all have this clock, right? When the clock rings, the particle is going to take a random walk step. Okay, so jump to the left or to the right, probability high. Okay, but there's the exclusion rule. Okay, so if this particle tries to jump to the right here, there is already a particle on there, so this jump will be prevented. That's the exclusion rule. Okay, So there's the exclusion process, if you like, this particle trying to do simple random walks, but they block each other, they can't step on the same sides. Okay? So I think all of you are more or less familiar with this exclusion process. So maybe one thing I should mention or recall is that this product of Bernoulli is an invariant measure for the exclusion. Okay, so it's as if the process has been running forever at time 0. Okay, it's the equilibrium. All right, so that's the environment. So that was the random walk. So I'm going to put the random walk on top of that. Okay, so I'm going to let me just add here. P0 is going to be the law of that process. Okay?
Sorry, I'm just going to read the letter that is.
Up there, it's a row. Sorry.
Yeah. It's a row. Okay.
Yeah. All right. Sometimes I will put the row on the measure. Sometimes I will put the row on the random walk, but hopefully it will be clear enough. Okay, so it's the measure associated just with the environment. Okay, so now for the random walk, I'm going to fix a realization of the environment. So I fix the whole history of the environment. Okay, so now I look at the quenched environment, and you define a Markov chain. So only on the quenched environment, Xn is going to be a Markov chain. Okay, in discrete time. You can define the same stuff in continuous time, but here I will do it discrete. Okay, you start your random walk at 0, and then what you're going to do, this random walk is also going to be nearest neighbor, and at time n is going to jump to the right with probability that depends on the state of the environment at the site of the jump and at the time of the jump. So it will jump to the right probability p full some parameter if there is a particle below xn at time n, and to the right probability p empty if there is no particle. All right, and here I need to tell you what are my parameters. So essentially I just want to choose p empty and p full to be non-degenerate. Okay, not 0, not 1. And then you see here I add that p empty is smaller than p full. It doesn't really matter because if you are in the other situation, just flip around z and you end up in a similar case. Okay, so you can assume that without loss of generality. Okay, but it's kind of important for us because I'm going to talk about monotonicity, so that will give you the direction of the monotonicity. Okay, and you jump to the left with the corresponding probabilities. Okay, so I'm going to draw a picture in a second to clarify the thing. Okay, so what's happening at time n? You have some at time n here on z. At time n, your exclusion process is in some configuration. Okay, and then say you random walk. So that's Pierre-François here. Pierre-François is on top of a particle, so you will jump to the right probability p full, and to the left probability 1 minus p empty. But if the random 1 minus p full, sorry. But if I was looking at another random walk, so here's Guillaume now, and Guillaume is on the empty side, so he will jump to the right probability p empty and to the left probability 1 minus p empty. All right, so you have a random walk that is using two laws, and which law he is using depend on the state of the environment at the time and the place of the jump. All right, so hopefully it's clear enough. I'm just going to draw an extra picture that was going to be key to a lot of things I'm going to say. So there is a graphical way of representing that process. Okay, so here I'm going to put z on the x-axis. I'm going to put time on the y-axis. Okay, so in the background, I'm not going to draw it everywhere, but in the background, you have your exclusion process running all the time. Okay, in continuous time, these particles are going to move around. Okay, and on top of that, you're going to have your random walk started at 0 that's going to do something. Okay, so you can always represent this process in this space-time picture, and every time you want to look at the walk at time n, you're just going to ask, okay, what's the state of the exclusion at that point in space and time, and it will tell you which law you have to use for your random walk. All right, and so I can right away point was the difficulty with this kinds of model is that you see that this dynamic random environment is creating correlation in the model. Okay, so if you observe your random walk here, it will give you information about the environment around the particle here, right? So this information is going to create correlations that are going to propagate space and time like that. Okay, so and these correlations are slow because the exclusion process mixes slowly. Okay, it has a quadratic mixing time, so it's hard to deal with, right? The correlations are going to decay at best like 1 over square root t, which is very slow. Okay, you can't apply Boyle continuity or this kind of stuff. It's too slow. Okay, so a lot of the hard difficulties are about dealing with these correlations. Something I should have mentioned also earlier is that these models exactly fall into the categories that are outside of what Felix and what Balint talked about in the last couple of days. Right? They had either reversibility or divergence-free model, and you could implement some general techniques. So here it's not reversible, it's not divergence-free. There's a priori no big technical tool you can use to try and hope to prove law of large numbers or CLT. Right? So it's more like hands-on techniques so far. Okay? So in particular, I mean, the best hope would be to find an environment seen from the particle, but so far nobody knows how to do it. We don't know if there's one. All right, so that's a hard question. All right, and I will mention that a couple of times during my talk. Okay, so these kinds of models have been studied for a long time, okay, both by physicists and by mathematicians. In probability, for a long time, they were looking at adjacent model. Okay, so either you change a little bit the environment. So one thing that people like to do is instead of looking at the exclusion, look at a system of independent random walks. It's more or less the same, but then the results that were proved, for example, by Den Hollander, Kestel, and Sidora-Vicius is a law of large numbers for the system where the density, when the density goes to infinity. Okay, so a weak law of large number when the density goes to infinity. So perturbative results. Then there was a long sequence of papers where they changed the environment, asked for better mixing properties. Okay, and they were able to implement some regeneration argument and prove law of large numbers. That's people in the Netherlands, Den Hollander, Avena, Vollering, Redig, all these people. And then there's also a long list of papers by Augusto Teixeira, Marcel Lario, Ryan Blondel, Dos Santos, Vladas Sidora-Vicius, where they prove also results for these random walks on top of this system of random walks, but again in perturbative regime, taking the density very high or very low, all right, which are cases where you can try to work out something. And there's a paper by François Veners and François Simonus where they look exactly at the model I defined. And again, it's perturbative, but this time they play on the rate of the exclusion. Okay, so they take it either very fast or very slow. Okay, and they're again able to prove law of large numbers and CLTs in the ballistic regime using some regeneration arguments. Okay, and a lot of that is also based on the older techniques of Snitman-Zerner, Komeit-Zeitouni with these regeneration structures. All right. So now what are the most recent results? So I need to quote one result from a few years back by Augusto Hilario, Advelo Ronche, myself, and Augusto Teixeira, Timba. That's 19, I think. Okay, and our point of view was to, okay, we wanted to prove a law of large numbers and CLT in some cases. And we wanted to see the speed as a function of the density rho. Okay, so fix all the parameters, fix PMT, P full, fix the density, fix the red, sorry, and play with the density. So what we proved that there exists a function V from 0, 1 to -1, so that will be your speed, deterministic, non-decreasing. So the non-decreasing, again, is a little bit key in all of what I am saying, and it relies on this inequality. But again, if you have the other inequality, it becomes non-increasing and everything is more or less the same. It's just this symmetric case. Okay, so there is this function such that you have a law of large numbers. For xn over n. Okay, under the annual measure. I forgot to talk about the two measures. Okay, but for a law of large numbers, it doesn't really matter. But so what's the annual measure? So here I said you fix the environment, that it gives you the quench measure of the random walk, p eta. When you fix the whole environment, then you can average over the environment and you obtain, that's the quench measure, and you obtain the annual measure, okay, which is the averaging of the quench measure over the environment. That's the annual. Okay, so most of you must already know about this kind of stuff, but now we all agree. Okay, so we have an annual law of large numbers, and so I insist on annual because we have also some CLTs. Okay, so we prove that for all rho in 0, 1, except at most two values, rho minus and rho plus. Okay, so I'm going to write the definition for rho minus and rho plus, but I will draw a picture which will be more informative. So rho minus is the supremum of the densities such that V of rho is negative, and rho plus is the infimum of densities such that V of rho is positive. Okay, so the picture that goes with that is the following. So here I put rho, I put V. Okay, and now I'm going to think about, so the result holds in more generality, but with the picture I'm interested in today is the one that you see in that case. Okay, so P empty is less than a half, P full is larger than a half. So that you have a chance to go in both directions. Okay, so if you do that, for very small density, you're going to be close to P empty, okay, most of the time, so you'll have a negative speed. Then what could happen is that your speed may jump from strictly negative to 0. Okay, that if that happens at rho minus, then you may stay at 0 speed for a while, and then at rho plus, you may jump from 0 to strictly positive. Okay, and what we're saying is that you have law of large numbers everywhere except where V jumps. Okay, and we don't have much information on V when it jumps, if it jumps. We don't know if it jumps, probably not. But if it jumps, we can't say much, except in some cases where I can prove more stuff and we're able to prove law of large numbers at one of these points. But in generality, no. All right, so in the same paper, we also add CLTs in the non-zero speed regimes. Okay, so usual diffusive CLTs around the limiting speed. I need, yeah. It's just from the regeneration structure. Okay, so it comes for free, essentially. Okay, but the zero speed regime. So here we have the law of large numbers, but we don't have the fluctuations, right? And that's actually a very hard question to understand the fluctuations in the zero speed regime, exactly because you would be in a situation where your correlations are becoming very annoying. Yeah.
But you know that there are at most two jumps or not?
At that time, well, we still don't know actually, but you know, yeah.
But actually, how do you define V? I mean,
okay, yeah. So I'm not going to talk about this paper in particular, but there is a deterministic function that is, you can define two quantities V plus and V minus that are always well defined, and then the paper proves they are actually equal, and that's what we call V. Okay, in terms of that distant limit of the walk when it converges. Right? So it exists, regardless of the fact if the law of large numbers holds or not. So that's a good point actually. And what was the question again?
I asked, was it there was.
Ah, yeah. No, we don't know, but you know, here you have your regeneration structure, right, that you define with François Simnos. And okay, if you change it a little bit, it looks like one could prove continuity in the non-zero speed regime. It's not proved because we need to change your regeneration. It's a bit of technical work, but I mean, there's no big doubt that there is no jump. But yeah, if there is a jump, it's here. I don't believe there is a jump, but if there is one, it's here. Okay? So I will talk more about the fluctuations here in a second. Okay? So I was really hoping that this flat bit was happening. Okay, why? Because I think it would have been a good indication of a transient zero-speed regime, the same kind of stuff you can see for random walk on static random environment dimension 1, right? Because you would have one density here where your random walk was recurrent, and then you increase a bit the density, you put yourself here, you're not recurrent anymore, you become transient, but you still have zero speed. Okay, so that would have been nice, that would have been a trap regime. Okay, it was really not clear if you look at the past literature if this trap regime could happen or not. It's pretty clear that the traps of the static case can't hold, okay? But that doesn't mean that there is no traps happening, okay? One trap failing doesn't mean that all traps are failing. So that was a very, to me, yeah, it would have been a good indication, okay? But unfortunately, so what we proved here with Pierre-François and Guillaume is that there is no such flat speed, okay? The speed is strictly monotonic. All right, so the new result I want to talk about. So the paper is not out yet, but it will be out very soon. I don't want to give any date anymore, but it should be in the next couple of weeks. And if it's not, then you have to complain to Guillaume and Pierre-François. Never to me, please. But, all right. So what we prove is that rho minus is equal to rho plus. And in particular, what we really prove that V is strictly monotonic. Okay, so we don't talk about the jumps. Jumps may still happen, but at least there is no flat bit. Okay, so now the picture, the worst case scenario would be something like one jump. Let me call that rho C. One jump at rho C that may or may not happen. Okay, and again, what's happening at rho C? You know nothing except if you're in a particular situation. So what kind of particular situation? For example, if P empty is equal to 1 minus P full. Okay, less than a half. Okay, so meaning in average, your environment, your random walk should be symmetric. Okay, then you can use some extra symmetric arguments. So actually, if there is a law of large numbers, then it could only be 0, and then result from Marcelo, Augusto, and myself prove that there is indeed a law of large numbers with speed 0 at density 1/2. In that case, right? Just in that case. Again, not in full generality. Okay, you need extra arguments. Okay. But again, the fluctuations here are very mysterious. Okay, and if you look at the physics literature, some people conjecture that the fluctuations may be super diffusive. Okay, so you can see different exponents. I think the most, the one I believe the most would be 2/3, right, or 1/2. So it's really not clear if it's super diffusive or not. But there is a hard question to think about here. Okay, the continuity is still not solved, but okay, we are working on that. Hopefully, I don't know, maybe next year's conference. We'll see. All right. So what I'm claiming, it was in the title of my talk, is that it's a sharpness result. Okay. So why am I pretending that it's a sharpness result? Because you can prove the following corollary. Okay. So look at the backtracking event for the random walk. Okay, look at the event where x hits minus n before 1. All right? Then you have two phases. You have one phase that is subcritical, where the probability under the n measure of Bn is going to decay very fast. Okay, so for technical reasons, I have a weird fast decaying function here. It's faster than any polynomial. Why it's that and not exponentially decaying is because of technicalities in the paper with Marcelo and Augusto. Okay, we didn't want to make our renormalization more complicated than what it was, so we settled on that. And that holds for all rho larger than rho C. Okay? And the second phase is property of Bn is larger than the constant if a rho is smaller than rho C. Okay, constant depends on the rho. Okay, so stated like that, it really looks like a sharpness result for a percolation model, right? So this will be the equivalent of a connection, covariant connection event, subcritical phase with a strong decay, and supercritical phase where you have a positive probability of connecting. All right, and again, there is a critical case, right? Rho is equal to rho c, where it's more complicated, where this property should be polynomial, but hard to study so far. All right. So okay, so it's not just a gimmick. Okay, I'm not just saying it's a sharpness result because it's a fancy topic these days. It's because the proof we are using are actually inspired by the proof from percolation theory, right? And in particular, this paper of Dumini-Copin. Just the philosophy of the proof, saying not the technical aspect. The technical aspect is very different, okay, because the two models are very different. Okay, but the general strategy is similar to that of Dumini-Copin, Goswami, Rodriguez, and Severo, where they prove the sharpness for the level cell percolation of GFF. So that's 23. Okay, and you have same authors with Augusto, where they prove a similar result for the random interlacement. Okay, and both papers are based on the same philosophy. Again, technically it's different than ours, but the strategy is more the same. So what's the general strategy of proving this kind of sharpness result following these blueprints? Is the following. So you have a model that has long-range correlations, okay, so hard to study, and you want to prove a sharpness result. Okay, so you think it's long-range correlation, but maybe if I define a finite range model, then I can prove all the sharpness I want. Okay, you can try to be quantitative, and that will be your first step. Okay, with good sharpness. Okay, and hopefully it will be not too hard to prove what you want to prove. Okay. Second, you compare the finite range model to the full range model. Okay, and then hopefully the good sharpness of the finite range model is going to translate into a sharpness for the full range model. Okay, so all of that has to be made precise, be made quantitative, but that's essentially the two-step strategy. All right, so I'm going to write two statements that encapsulate that. First, I'm going to define the finite range model. Okay, so the finite range model, I'm going to define it here. So there is a natural candidate for the finite range model here, right? So as I said, in this space-time picture, the problems come from the fact that this dynamic environment is creating correlations in your space-time picture, okay? So one thing that you could say is that, okay, fix a range L, okay, that's the range, and every L steps in time, I'm going to fully refresh the environment, start again from the invariant measure. Okay, regardless of what happened in the past, I throw again my Bernoulli, IID Bernoullis on Z. Okay, and you do that every time multiple of M. Alright, and here clearly is going to create a finite range model. Why? Because now, okay, your random walk starts working. It does the same as before. It still looks like the random walk on the exclusion process, but arrives time L, wherever you are, you pick again around the position a fresh environment, and you start afresh. Okay? And pop, you keep on walking. Okay, so if you do that, clearly, these blocks here are going to be IID blocks of finite size L, so you have law of large numbers, CLT, everything you want. All right? So it should be sharp in a good way. Okay, you'll see in a second that it's not that easy actually, but at least what's easy is that I'm going to call that xn rho. So I'm going to put rho, the density, as subscript in the random walk because I'm going to play on the density a little bit. And I put the L for the range of the walk. Okay? The range of the dependence. Okay? So what's very easy to prove is that x rho L at time n divided by n converges almost surely under the any measure or whatever measure to some speed VL of rho, and there's even a formula for VL of rho is just the expected increment at time L divided by L. Here's the expectation of one term in your law of large numbers. Okay, so that's the value of the speed for a finite range. Now let me add something right away. Here I've put the expectation of displacement of the finite range model at time L. But you see at time L I have not refreshed the environment yet. Okay? So actually I can forget the L, right? It's the same expectation as for the full range model. Okay? So just a remark that will be meaningful later. Alright. Okay, so that's the finite range model. Now what are the two results that I want to prove in order to be able to prove the main theorem? Okay, so first, proposition to call approximation. Okay, so it's the fact that the speed of the finite range model is close enough to the speed of the full range model. Okay, so what I'm going to prove or argue is that is the following. All rho, large, but depending on finite parameters, and alpha L is something small that goes to 0. So here, if you want to be precise, you can take log to the 100 L over L, whatever, so some small quantity. Okay, it doesn't really matter. Okay, the 1 over log L is just also some small quantity. So what I'm saying here is that the speed of the full range model is well framed by the speed of the finite range model. But okay, you have to add a little bit of density for the finite range model on the right-hand side and add an error term. It's going to 0 with L. And the same kind of stuff on the left-hand side, right? So you have to decrease a little bit the density of the finite range model, remove some mistake, and you can have these good inequalities. Okay? So that's the step 2 of the strategy there, is comparing the full range model and the finite range model. Okay, so it's not easy to prove, but it's not the hardest part. And the hardest part is actually proving a quantitative monotonicity, so let's say QM, quantitative monotonicity for the finite range model. So what we want to prove is that if you increase the density by some value epsilon, then it has to have a noticeable effect on the speed of the walk. Okay, and we really don't ask for much here. We ask that it's larger than 3 alpha L. So why we're not asking for much? Because this alpha L is going to 0 with L. Okay, L is fixed, but you know, if you had in mind, okay, you just take L to infinity, the speed is going to approach V of rho, but here on the right-hand side it will go to 0, so the stuff will not be enough. Okay? Just this one on its own is not enough. And that's for all rho in 0, 1, all epsilon in 0, 1. Well, you know, you need a rho plus epsilon less than 1 as well, but that's it. All right? Okay, so that's it. Once you have these two results, you can conclude. Yeah, I mean, you need that. That's what you mean.
I mean, the lower value comes to 0. Otherwise, I can just take epsilon to be 0.
For L large enough. Right. Okay. So yeah, the smaller epsilon is the larger L has to be. All right. All right.
What is the analogy? For random interactions, it would be to play with this U parameter? Or?
For the GFF, we'll be playing on the level of the level set percolation. Well, yeah, for the interlacement, I guess it would be the U, the intensity. Right, so this kind of, you can see that, so it's based on the sprinkling techniques, right? So usually it's used to decorrelate the environment. Here we're not exactly using it for decorrelation, but we are using it for Well, it's a sort of decoration, a mixing, or yeah, a mixing of the environment as time goes by, locally around the random walk. Okay, so once you have these two statements, it's very easy to prove the main theorem. Why? Well, you look at V of rho plus 3 epsilon. You use the approximation that's larger than VL of rho plus the 3 epsilon minus 1 over log L minus alpha L. Okay, this thing just by, so that's the approximation. Now I'm going to use, okay, one thing I should have mentioned as well. The non-strict monotonicity is easy, right? The non-strict one, both for the finite range model and the full range model. Why? Because on this space-time picture, okay, what you can do is to say, okay, you can compare a environment with density rho, have your random walk on top of that, and then couple an environment with density rho plus epsilon. So effectively how you do it, you sprinkle a little bit the environment, meaning you add a little bit of red particles here and there. Okay? And now instead of doing the exclusion, you do the interchange process where you change the state of two neighboring vertices. It will be the same process. They are equivalent. If you don't distinguish the particles, it's the same processes, and you do that, right? And now you're going to define the red random walk on top of the larger environment, and it's going to follow the same trajectory as the blue environment, except if there is a site where there is a sprinkler. And at that position, the only thing that the red trajectory can do is step on the right while the blue steps on the left, right? But it will never be the other way around. Every time they meet again, they will stick together and the red will never cross to the left. Okay, so the non-strict monotonicity is easy, right? So I should have mentioned that earlier. So anyway, that's what I'm using in this step. Okay, provided that L is large enough so that this thing is less than epsilon. Now this thing you're going to use the quantitative monotonicity. I'm losing an epsilon in the density, but I'm winning 3 alpha L. And again, I'm going to use the non-strict monotonicity, okay, 1 over log L plus 2 alpha L. And I'm going to use my approximation. So now that's larger than V of rho plus alpha L. I'm using 1 alpha L, and that's strictly larger than V of rho. Okay, and that's the strict monotonicity I wanted. Okay, so anyway, once you have these two statements, that's easy to conclude. All right. So now, okay, I have good time. So I'm going to give you an idea of how to prove the approximation. Okay, how to compare the full range model and the finite range model. So the other part, the quantitative monotonicity here, even though it looks like it's a statement on the finite range model, well, in the end you have to study this expectation. This expectation is about the full range model actually, right? Because you look at the expectation up to time L where the environment is not refreshed. So understanding this VL of rho is actually not easier than understanding the full range model, okay? So we have to do, the advantage that you have is that you look at finite horizon, and we are not asking for much, right? So the proof of this quantitative modality is actually the hardest bit in the paper. Okay, so maybe I will draw a picture at the end to explain roughly what we do, but I'm not going to go into the details.
Yeah, I'm a bit confused now by the overall message, because the first proposition was to say I have this infinite range model, and
yeah.
I'm comparing it with the finite range model.
Mm-hmm.
And now you are saying that the second proposition is actually also about the infinite range model.
Yeah, because if you look at this expectation, right? So
I agree.
right, it's that, but you can remove the L, and then in the end it's the same stuff. right? So if you want to prove something precise about that, then it's hard, right? And this would qualify as a little bit precise, right? But what we win is that we are looking at finite horizon, right? Okay, so this alpha L, even though it goes to 0 with L, if you fix L as large as you want, but fixed, this will still be positive, right? Small. Okay, so so it's a statement about the full range model, but for the full range model, it would make no sense. So it wouldn't be useful on this one because this right hand side goes to 0, right? So we really have to use the comparison between the finite horizon and the full range model. Okay, so how do you prove the approximation? So now my goal is to explain how to prove. So I'm going to explain just one of the inequalities. The other one is very similar. So let's look at V of rho larger than Vl of rho minus 1 over log n minus alpha L. All right, so I want to prove that. So first, the statement is going to be implied by the following. So if I look at the probability that x rho x rho n is smaller than VL of rho minus, so let me call that rho 0 right away. Okay, so rho 0 is this rho minus 1 over log n. Okay, rho 0 minus alpha L times n. We want that to go to 0 with n. Okay, so if that's the case, we know that the law of large number holds. Okay, you can think of a row where the law of large number holds, but actually that's true for any row, what I'm going to say. So if this quantity, if this probability goes to 0, it means that this quantity has to be smaller than V of rho. Okay, otherwise you would have a decent chance to be slower than the speed, larger than your speed. Right? Okay, so this probability going to 0 implies this inequality. Okay, because you will have no chance to go slower. Okay, so what I'm going to do now is, instead of looking at time n, I'm going to look at times that are d-adic. Okay, so 2 to the n L, where L is fixed. Okay, so and now what I'm going to try to do is the following. So I'm going to look at your model. So we're looking at the full range model at some very large time, 2 to the n L. Okay, and I have the full range model. Okay, and now we're going to say, okay, we want to study this probability for this full range model. So what I'm going to do, I'm going to compare the behavior of the full range model to the model with range 2 to the n minus 1 L. Okay, so just a random walk that walks the same walk. But then, whoop, here its environment is refreshed, and now maybe it does something different. Okay? Okay, now I'm going to compare this model with range 2 to the n minus 1 L with a random walk with range 2 to the n minus 2 L. So now I'm going to look at the third walk. Okay? That refreshes at all these other time steps, right? So it will follow the same, then refresh here, okay, then refresh again, and refresh again, okay? And I'm going to keep on doing that, okay? So compare the full range model to the 2 to the n minus 1 L model, 2 to the n minus 2 model, all the way down to L, okay? So, and hopefully each of those pairs of models will be close together, and I will be able to prove something. Okay, so it's just to explain the expansion I'm going to write now. Okay, so I want to look at the limit of that probability. Okay. Okay, so I want to look at the limit of that. Okay, by non-strict monotonicity, I can replace this rho by some rho n that depends on n. Okay, as long as rho n is smaller than rho, because if I decrease rho, I make this the probability only more likely, okay, larger. So this, if this goes to 0, this goes to 0. Okay? Okay. And now I'm going to add another term also, which is going to be the probability that x rho 0, so this rho 0 here, which L and L, smaller than the L of rho 0 minus alpha L over 2, say, 2nl. Okay, so instead of looking at the limit of just that term, I'm going to look at the limit of this difference. Why I can do that? Because I know that this term is going to 0 with n. Why? Because this speed here, this thing, is strictly smaller than VL of rho 0, and I'm looking at the deviation event for the L range model at density rho 0. Okay, so this probability goes to 0 for free, okay, by definition of VL of rho 0. Okay, so this difference, if this difference goes to 0, this term goes to 0. Okay, and now what I'm claiming, I mean that's not too hard, is that this probability you can bound it by the following event. Okay, if you have a coupling measure where you can couple this random walk and this random walk, then you can write that as and you want that to be smaller than minus alpha L over 2 to n. Okay, so why? It's because if you have a coupling measure, these two measures are going to be the same. And you'll be able to define both walks as the same measure and just use this inequality that provides this one. Okay, and now I'm going to use my expansion. I'm going to write an expansion. So I'm going to take my scale L to L, to K L, so that's going to be all the scales I'm going to look at. Okay, and as I go from scale to scale, as I go from the L range model to the 2L range model to 4L range model, I'm going to slowly increase the density. Right? So let me check it's increasing. I think it's increasing. It's increasing. So I'm going to take a sequence of rows. So I already have rho 0. I'm going to define rho k plus 1 is equal to rho k plus some small increment epsilon k. It doesn't really matter what it is. I think we chose, that doesn't matter. Some big power of log to k to the kl. But what you want is that this thing stays lower than for all k. Okay? So this series, this sequence is going to converge to some limit that stays smaller than rho. Okay, that's going to help me to increase this density. Is going to help me to do this sprinkling techniques. Okay, and now what you can write? Well, you write an expansion for this difference, right? So that's why I'm comparing the different models with one scale being the double of the, one range being the double of the previous range. Right? Okay, and want that to be smaller than minus alpha L to n. Okay? And one thing maybe I should mention again is that here, okay, I have the full range model, but you can always see it as the finite range model with range 2 to the NL because we observe it only up to time 2 to the NL, so it doesn't matter if you refresh it or not. Right? Okay, so that's a simple expansion. Okay? So now the goal is to understand these terms. Okay, so this probability here. So I didn't tell you what the coupling measure, okay, and it's going to be the whole game of the end of the proof. But one last technical thing I need to write is that this probability here, it's smaller than the sum for k equals 0 to n minus 1. So I'm just using a union bound and an estimation. Okay, so x rho k plus 1 to k plus 1 L to NL minus x rho k to KL to NL smaller than, okay, smaller than doesn't really matter what, but I think we took log to the 99 to KL over 2KL times 2NL. It doesn't really matter, something small. And why it's true, because if you sum all of these guys, then it would end up something smaller than alpha L over 2. Okay, it's a small computation, tedious, but everybody can do it. Okay, provided that L is larger than 10 to the 10 or something. All right, so now the game is to understand the probability of this deviation being small. Okay, so now if you look at this term, okay, you know that this model refreshes every step to KL. Okay, think n larger than k, right? So you refresh every time to KL, refresh every steps to k plus 1L. So in particular, both refresh every 2k plus 1 L steps. Okay, both at the same time. So what I'm saying is that this difference is actually the sum of IID terms of what, 2n minus k minus 1 terms, IID, and distributed like x 2k plus 1L, rho k. So I'm going to, instead of rho k plus m, I'm going to write rho k plus epsilon k 2 times 2kl minus x 2kl rho k 2k. Okay, so I want to prove a deviation probability about the sum of IID random variables where each term are distributed like that. Okay, so if I control the expectation and the variance of this term, I can apply Chebyshev. This term is going to be smaller than 1 over n squared. Sum smaller than 1 over n, this goes to 0. Okay, so the goal is to control the expectation and the variance of this guy. Okay, and you want to prove that it's not too negative. Okay, so we're really not asking much. Right, so I'm going to stop in 2 minutes. I'm just going to draw the last picture that explains how you do that. Well, you're going to define your coupling measure where you're going to couple. So I'm just going to write L, Lk for 2 to the k L. Okay, so here you have Lk. Oh, let's write 2 to the k L. And here you have 2 to the k plus 1 L. Okay, so how do you compare the work on density rho k and the work on density rho k plus epsilon k? Right, at time 0 you're going to do the natural coupling where you're going to ask for all the particles of rho k to be covered by a particle of rho k plus epsilon k. Then you have extra particle for the blue environment, but that's fine. Okay. So you have your everywhere where there is a blue particle, there is a red particle, and you have extra red sprinklers. Right? Now, from time 0 to the KL, you're just going to ask your two random walks to work their natural law. Okay, and here on the picture, I'm going to pretend that this walk just follows the same path. Okay, so here in red, it's x rho k to KL. And here in blue, it's x rho k plus epsilon k to k plus 1 r. Okay, so actually the blue path could step more on the right, but let's forget about it. Okay, it's the worst case scenario. Okay, okay. Now what happens at this time? Well, now at this time, which environment is refreshing? The red environment is refreshing, but not the blue one. Okay, okay. So I have my blue particles, but the red particles now are going to be picked again from the invariant measure, and I cannot ask anymore them to be covered by the blue particle, okay? Because that would violate their law, okay? Because you're not from the invariant measure for the blue environment, okay? So essentially, you don't control much at that time. You don't know, you can't really compare the two environments, okay? So at that point, the two walks start to work independently. So worst case scenario, so the worst case scenario for me is this one, where the blue guy goes straight to the left and the red guy goes straight to the right. Okay, and what you can do, on the other hand, is try to use these Sprinkling techniques, okay, which says like within time t, okay, as long as these two environments are well distributed, they have a good density, a good empirical density, okay, at some given mesh, I can use some mixing and try to cover the red environment seen from this position by the blue environment seen from this position, okay, even in the quench setting. Okay, so that's the new thing that we had to do. We had to prove such result for the quenched situation. Okay, so that's very close to what people like Popov and Teixeira did in the soft local times, or Baldassare and Teixeira did for the exclusion process, but they did it from the invariant measure. So here we're just using the empirical density of the processes of the environment, and we're able to reprove it. Okay, and if you're able to do that, okay, the environment seen from the blue guy here is the same as the environment seen from the red guy here. And you're happy you can couple them again. And the worst that you have lost here is this small time t. So all you have to do is to manage to do it within a time that is logarithmic in 2 to the kl. Okay, and that's something we can do. All right? And yeah, so that's the kind of strategy we use for the proof. For the quantitative monotonicity, it's a more complicated strategy, but it's using heavily as well the fact that you can remix the environment around the particle, which is the hard part, because again, you're not in the environment, in the invariant setting. The environment around the particle is not invariant, so you have to only use gross information about the environment to be able to do this mixing around the particle. And I'm going to stop here. Thank you.
Thank you. We have negative time for quick questions.
It's not negative yet. 1 minute 20.
Oh, a quick question. We have negative. Yeah, yes. How much is it important for you to have a diffusive environment?
It is important. Okay, for the low version, for the first paper, Augustin and Marcel, it's not that important. There are other stuff that could work, right? So weaker. Yeah, I think it's more crucial. You want that everything is mixing fast enough, and quadratic is just about fast enough. I think you could maybe do it a bit slower, probably, but not much slower. No? Yeah.
I think you can do it much slower with the conditions we have. Like this t is going to be a polylogarithmic of big L.
Yeah.
I mean, you can have something like cubic, I mean, much lower.
Yeah, but it will stay a polynomial thing, right?
Okay, I think negative time is over. Thank you.